Right now, you're living inside an invisible force field. Most people think space between planets is empty. That assumption misses the most important shield protecting your existence. Tonight we're discovering what happens when our sun fights the galaxy. You'll hear how this cosmic battle creates the boundary that makes life possible. Before we dive into this invisible protection, drop a comment about where you're listening from. If you enjoy these journeys to the edge of space, consider subscribing. These explorations of our cosmic neighborhood are meant to be shared. The sun has been hiding something from you. Every second, it blasts millions of tons of matter into space. This isn't gentle starlight. It's a hurricane of electrically charged particles racing outward. Scientists call this the solar wind. That name sounds peaceful. The reality is violent. The sun's outer atmosphere gets unimaginably hot. That heat rips apart every atom it touches. When atoms get ripped apart, they become electrically charged particles. Scientists call this mixture plasma. Think of it as a soup made of electric sparks instead of vegetables. This electric soup can't stay still. The sun launches it outward at nearly 1,000,000 miles per hour. That's fast enough to circle Earth in 3 minutes. The solar wind doesn't stop at the planets. It keeps racing far beyond everything we know. As it travels, it carries the sun's magnetic influence with it. Together, they blow up an enormous invisible bubble around our entire solar system. We live inside this cosmic bubble. Scientists call it the heliosphere, literally the sun's sphere. Something extraordinary happens at the edge of our neighborhood. The solar wind races outward for billions of miles. Then it finally meets something that can stop it. Space between the stars isn't empty. It contains thin clouds of gas and dust. Dangerous high-energy particles zip through this region. Scientists call these cosmic rays. They're like bullets made of energy that can damage living cells. The solar wind has been pushing against this interstellar stuff. The collision creates a sharp boundary. On one side sits everything under our sun's protection. On the other side lies the dangerous galaxy beyond. This boundary forms like the surface of a soap bubble. The solar wind can't push any further. The interstellar material refuses to give ground. Two cosmic forces locked in eternal stalemate. Our solar system exists as a protected island floating through the galactic ocean. This boundary is the only thing standing between Earth and deadly radiation from deep space. The solar wind has been racing through space for years. Nothing has slowed it down. It travels faster than the speed of sound in space. Then something incredible happens at the edge of our solar system. The solar wind crashes into the interstellar material. This collision creates what scientists call a termination shock. Think of it like a traffic jam in space. Cars moving at highway speeds suddenly hit gridlock. The solar wind goes from supersonic to subsonic in an instant. Supersonic means faster than sound. Subsonic means slower than sound. The change happens across a boundary that stretches around our entire solar system. This cosmic traffic jam creates a massive shock wave. The shock wave heats up the solar wind. It compresses the particles together. Everything gets squeezed and slowed down. The termination shock marks where our sun's power begins to fade. Beyond this point, the solar wind becomes a different beast entirely. Past the termination shock, the solar wind enters a strange new realm. The particles are no longer racing freely through space. They're getting pressed and heated by forces from all directions. Scientists call this region the heliosheath. Think of it as the squeezed part of a balloon. When you squeeze a balloon, the air inside gets compressed and hot. The same thing happens to the solar wind here. The compressed solar wind creates turbulence. The particles swirl and churn like water in a washing machine. Magnetic fields get twisted and tangled. Nothing moves in straight lines anymore. This turbulent zone acts like a buffer between our solar system and interstellar space. The solar wind particles bounce around chaotically. Some get turned back toward the sun. Others eventually escape into the galaxy. The heliosheath transforms our sun's orderly wind into cosmic chaos. This chaotic boundary layer protects us by absorbing and deflecting dangerous particles from deep space. At the very edge of our cosmic protection lies the final boundary. Here, the weakened solar wind faces off against the interstellar wind. Neither force can overpower the other. They reach a perfect stalemate. Scientists call this boundary the heliopause. It's like the ultimate property line in space. Everything on one side belongs to our sun. Everything on the other side belongs to the galaxy. The two winds don't mix. They press against each other across a contact surface. The solar wind particles stay on our side. The interstellar particles stay on theirs. It's like oil and water refusing to blend. This contact surface moves and shifts over time. When the sun gets more active, it pushes the boundary outward. When the sun calms down, the boundary moves inward. The heliopause breathes like a living thing. This final boundary completes our cosmic protection system. The heliosphere surrounds everything we know with multiple layers of defense against the hostile galaxy beyond. The answer takes us to the most dangerous neighborhood in our solar system. The sun's outer atmosphere is a place where normal matter cannot exist. Temperatures here reach over 1 million degrees Fahrenheit. That's hundreds of times hotter than the sun's visible surface. This hellish environment does something incredible to ordinary hydrogen atoms. The heat rips apart every single atom it touches. Hydrogen atoms have one proton and one electron. The extreme heat tears them apart completely. What remains are free protons and free electrons flying around separately. Scientists call this state plasma, the fourth state of matter. Solid, liquid, gas, then plasma. Most people never see plasma on Earth, but it's the most common state of matter in the universe. This plasma soup cannot stay trapped near the sun. The extreme heat gives these particles enormous energy. They start racing outward at incredible speeds. The sun's corona becomes a launch pad for the most massive wind in our solar system. Most of the time, the sun's magnetic field acts like a cage. Magnetic field lines loop back to the sun's surface. They trap the hot plasma in huge arcing structures. These loops can be bigger than entire planets. But something dramatic happens in regions called coronal holes. These aren't actual holes you could see with your eyes. They're areas where the sun's magnetic field lines don't loop back. Instead, they stretch out into space like open roads. When plasma hits these open magnetic highways, it accelerates dramatically. The particles race outward much faster than normal solar wind. This creates what scientists call fast solar wind streams. These streams can reach speeds of hundreds of miles per second. The fast solar wind carries the sun's magnetic influence far into space. It creates a magnetic connection between our star and every planet in our solar system. The sun's magnetic field becomes the solar system's magnetic field. The solar wind doesn't travel in straight lines from the sun. Our entire solar system rotates like a giant carousel. The sun spins. The solar wind gets caught up in this cosmic rotation. As the solar wind streams outward, it creates a spiral pattern. Think of a garden sprinkler spinning while it shoots water. The water doesn't go straight out. It curves into a spiral. The solar wind does the same thing in space. This spiral pattern carries the sun's magnetic field throughout our solar system. Scientists call this the interplanetary magnetic field. It's like a massive magnetic web connecting every planet to our star. The interplanetary magnetic field gets weaker as it spreads outward, but it never disappears completely. Even at the edge of our solar system, you can still detect the sun's magnetic signature. Our star's influence reaches much farther than its light. Different parts of the sun create different speeds of solar wind. Fast streams race ahead of slow streams. Eventually, the fast wind catches up to the slow wind in front of it. When this happens, cosmic traffic jams form in space. These collisions create what scientists call corrotating interaction regions. The fast solar wind slams into the slow solar wind. The impact compresses both streams together. Particles get squeezed and heated. The compressed region becomes denser and more magnetic than normal solar wind. It forms walls of enhanced particles and magnetic fields. These walls sweep through our solar system like cosmic bulldozers. When these interaction regions reach Earth, they can disrupt our planet's magnetic field. They cause geomagnetic storms that affect satellites and power grids. The sun's internal conflicts become our technological problems. Jupiter and Saturn have powerful magnetic fields of their own. These planetary magnetic bubbles create barriers that the solar wind cannot easily penetrate. The result is a cosmic collision between two magnetic forces. The solar wind gets deflected around these planetary magnetic shields, but some solar wind particles find weak spots in the magnetic defense. They spiral down toward the planet's poles following magnetic field lines. When these high-energy particles hit the planet's atmosphere, they create light shows. On Earth, we call them the northern and southern lights. Jupiter and Saturn have their own versions of aurora that dwarf anything seen on our planet. These interactions also trap solar wind particles around the giant planets. The trapped particles form radiation belts, dangerous zones of high-energy particles orbiting the planet. The solar wind that started peacefully at the sun becomes a hazardous environment around distant worlds. For billions of miles, the solar wind has been racing faster than sound can travel in space. This creates a special condition that scientists call supersonic flow. Supersonic means faster than sound waves, like a jet breaking the sound barrier on Earth. But physics has rules that cannot be broken. When the solar wind hits resistance from interstellar space, those rules kick in with dramatic force. The collision creates what scientists call a termination shock. Think of a highway where cars suddenly hit heavy traffic. The cars behind don't know about the slowdown yet. They keep racing forward at full speed. Then they slam into the traffic jam ahead. The termination shock works exactly like this cosmic traffic accident. Solar wind particles racing at supersonic speeds suddenly hit a wall of resistance. They have no choice but to slow down to subsonic speeds. Subsonic means slower than sound. This speed change doesn't happen gradually. It occurs across a sharp boundary that surrounds our entire solar system. The termination shock transforms the nature of the solar wind in an instant. Fast becomes slow, order becomes chaos. The solar wind emerges from the termination shock completely changed. It's no longer racing freely through space. Instead, it's getting squeezed from all directions by the pressure of interstellar space. This squeezed region has a scientific name that's hard to pronounce: the heliosheath. Think of it like the crushed part of a soda can. When you squeeze a can, the space inside gets smaller and the contents get more crowded. The compressed solar wind starts behaving chaotically. Particles swirl around in random directions. Magnetic fields get twisted into knots. Scientists call this turbulence, like water churning in a washing machine. The turbulent motion heats up the solar wind even more. Random collisions between particles generate extra energy. The heliosheath becomes a hot, chaotic buffer zone between our ordered solar system and the alien environment beyond. This turbulent layer serves as our cosmic shock absorber. It takes the organized energy of the solar wind and turns it into random motion. The chaos protects us by weakening the solar wind's ability to push back against interstellar pressure. Most boundaries in nature involve mixing. Rivers mix with oceans. Gases blend together in the atmosphere. But the edge of our solar system defies this normal behavior. Two completely different plasma flows meet and refuse to mix. The weakened solar wind reaches its absolute limit at a boundary called the heliopause. Here it encounters the interstellar wind flowing between the stars. Neither wind can overpower the other. They reach a perfect stalemate. The two plasma flows press against each other across a contact surface. It's like two people pushing against opposite sides of a door with equal force. Neither side moves. The door stays perfectly still. This equilibrium creates the cleanest boundary in our solar system. Solar wind particles stay on our side. Interstellar particles stay on theirs. The contact surface acts like an invisible membrane separating two different worlds. The heliopause marks where our sun's influence finally ends. Everything inside belongs to our solar system. Everything outside belongs to the galaxy. This boundary defines the true edge of our cosmic home. Our solar system doesn't sit still in space. It races through the galaxy at tremendous speed. This motion through interstellar space creates aerodynamic effects, just like a car driving through air. The heliosphere gets stretched behind us like the tail of a comet. The front of our cosmic bubble stays rounded and compact, but the back end gets pulled into a long, narrow tail stretching behind our solar system. Scientists call this the heliotail. It extends for hundreds of times the distance from Earth to Pluto. The tail contains solar wind particles that have been swept backward by our motion through the galaxy. This asymmetric shape makes our solar system look like a cosmic teardrop flying through space. The round head faces our direction of travel. The long tail streams behind us like a banner marking our passage through the galaxy. The heliotail shows that our solar system is not a perfect sphere floating in empty space. Instead, it's a dynamic structure shaped by our high-speed journey through the interstellar medium. Our solar system moves through interstellar space at over 50,000 miles per hour. The interstellar medium cannot get out of our way fast enough. This creates pressure waves that race ahead of our solar system. These pressure waves form what scientists call a bow shock. It's exactly like the wave that forms in front of a boat speeding across a lake. The water gets pushed aside and compressed into a wave pattern. The bow shock compresses the interstellar medium before it reaches our heliosphere. This compression changes the properties of the material we're about to encounter. It gets denser, hotter, and more turbulent. The compressed interstellar medium creates an additional boundary layer ahead of our solar system. This gives us advance warning of changes in the galactic environment. The bow shock acts like our cosmic weather forecast system. Our solar system plows through the galaxy like an icebreaker ship cutting through frozen water. The bow shock is our cosmic snowplow, clearing and preparing the path ahead for our journey through interstellar space. Voyager 1 was racing through the outer reaches of our solar system when its instruments detected something unprecedented. the solar wind speed suddenly dropped. The magnetic field strength jumped dramatically. Scientists had been predicting this moment for decades. The spacecraft had crossed the termination shock. This was the first time any human-made object had directly measured this cosmic boundary. The termination shock was no longer just a theory. It was scientific fact. Voyager's instruments recorded the exact moment when supersonic solar wind became subsonic. The data showed a sharp transition happening across a relatively narrow region. The boundary was much more defined than scientists had expected. The measurements confirmed everything scientists had predicted about this cosmic traffic jam. Solar wind particles really did slow down dramatically. Magnetic fields really did get compressed and tangled. The termination shock behaved exactly like the theoretical models suggested. This historic crossing marked humanity's first direct contact with the complex architecture of our cosmic protective bubble. Voyager 1 had become our scout, sending back reports from the frontier of our solar system. Voyager 2 followed a different path through our solar system than its twin. When it reached the termination shock, the readings looked nothing like Voyager 1's data. The boundary was in a completely different location. This discovery revealed that our heliosphere is not a perfect sphere. It's lopsided, squashed, distorted by forces scientists didn't fully understand at the time. The termination shock was closer to the Sun in some directions and farther away in others. The asymmetry comes from the Sun's magnetic field and our motion through interstellar space. Our solar system's magnetic field has north and south poles, just like Earth's magnetic field. These poles interact differently with the interstellar environment. Voyager 2's path took it through the southern hemisphere of our heliosphere. Voyager 1 traveled through the northern hemisphere. The two spacecraft revealed that our cosmic bubble has a complex three-dimensional structure that changes with direction. The discovery shattered the simple picture of a symmetric soap bubble around our solar system. Instead, we learned that our protective barrier is a dynamic, asymmetric structure shaped by invisible forces operating on cosmic scales. For the first time in human history, we had spacecraft operating in interstellar space. The environment beyond our heliosphere was no longer a mystery. We could measure it directly with scientific instruments. Voyager 1 crossed the heliopause in 2012. Voyager 2 followed in 2018. Both spacecraft sent back data from the alien environment between the stars. The interstellar medium was colder, denser, and more magnetic than scientists had expected. The transition across the heliopause was surprisingly sharp. The density of particles jumped dramatically in just a few months. The temperature dropped. The magnetic field orientation changed completely. Two different worlds separated by an invisible boundary. The Voyagers detected cosmic rays that had been mostly blocked by our heliosphere. These high-energy particles from deep space finally had direct access to our spacecraft instruments. The measurements revealed how effective our cosmic bubble really is at protecting us. Both spacecraft continue transmitting data from interstellar space. They're humanity's first permanent residence in the galaxy beyond our solar system. Their signals carry direct measurements from a realm that was purely theoretical just decades ago. The Voyagers didn't just measure particles and magnetic fields. They also analyzed the chemical makeup of interstellar space. This revealed what kind of cosmic environment our solar system calls home. The spacecraft detected hydrogen and helium in specific ratios. These measurements told scientists about the history and evolution of our local interstellar neighborhood. The gas cloud we're traveling through has been processed by previous generations of stars. Heavy elements created by ancient stellar explosions were mixed into this interstellar material. The chemical signatures revealed a complex history of star formation, stellar death, and galactic recycling. Our local cosmic environment has been shaped by billions of years of stellar evolution. The measurements also revealed how our heliosphere filters this interstellar material. Some elements penetrate our cosmic bubble more easily than others. The chemical composition inside our heliosphere is slightly different from the composition outside. This chemical analysis gave us our first direct measurement, what exists in the space between stars. The Voyagers had become our cosmic chemists, analyzing samples from the galactic ocean surrounding our solar system island. Both Voyagers are now more than 45 years old. They're operating with 1970s technology in an environment no engineer could have fully anticipated. Yet they keep transmitting scientific data across billions of miles of space. The spacecraft were designed for a 4-year mission to study Jupiter and Saturn. Instead, they've become humanity's most distant explorers. Their extended mission in interstellar space was never part of the original plan. It's become an unexpected bonus for science. Each Voyager carries a nuclear power source that slowly decays over time. The available power decreases every year. Mission controllers must carefully manage which instruments stay active. They're making difficult choices about what science to prioritize. The data transmission gets weaker as the spacecraft travel farther from Earth. It takes over 20 hours for a signal from Voyager 1 to reach us. The communication link becomes more challenging every year as distance increases and power decreases. These spacecraft represent humanity's first permanent presence in interstellar space, long after we lose contact with them. The Voyagers will continue traveling through the galaxy carrying messages from Earth to any civilization that might find them millions of years from now. Right now, our entire solar system is flying through a vast cloud of gas and dust. This isn't empty space. It's a specific region of the galaxy with its own properties and history. Scientists call it the local interstellar cloud. This cloud extends for many light years in all directions around us. A light year is the distance light travels in 1 year. That's an almost unimaginable distance. Yet this cloud is so large that it takes our solar system thousands of years to cross it. The cloud has its own temperature, density, and chemical composition. These properties directly affect the size and shape of our heliosphere. When the cloud gets denser, our cosmic bubble gets compressed. When it gets thinner, our bubble expands. We're not just passengers flying through this cloud. We're actively interacting with it every second. The cloud pushes against our heliosphere from all sides. Our heliosphere pushes back against the cloud. The local interstellar cloud acts like a cosmic mold that shapes our solar system's protective barrier. Our heliosphere exists only because this specific cloud provides exactly the right amount of resistance to contain our solar wind. Magnetic fields from 2 different sources are colliding at the edge of our solar system. Our sun's magnetic field carried by the solar wind meets the magnetic field that exists in interstellar space. The result is a cosmic wrestling match. Magnetic fields cannot simply pass through each other like light rays. When they collide, they interact in complex ways. They can twist around each other. They can snap apart and reconnect in new patterns. Scientists call this magnetic reconnection. When magnetic reconnection happens, it releases enormous amounts of energy. This energy accelerates particles to incredible speeds. Some of these particles get shot back toward our solar system. Others get launched deep into interstellar space. The boundary between our solar system and the galaxy becomes a dynamic zone of magnetic activity. Invisible field lines stretch and break and reform constantly. This creates a constantly changing environment at the edge of our cosmic home. The magnetic entanglement generates phenomena that scientists are still trying to understand. Our heliosphere doesn't just block interstellar material. It actively wrestles with the magnetic forces of the galaxy itself. Most interstellar material gets stopped at our heliosphere's boundaries, but one type of particle ignores our cosmic defenses completely. Neutral hydrogen atoms flow right through our protective bubble as if it doesn't exist. Neutral hydrogen atoms have no electric charge. They're just protons and electrons stuck together in perfect balance. Because they have no charge, magnetic fields cannot grab them or deflect them. They coast through space in straight lines. These atoms stream into our solar system from interstellar space. They pass through our heliosphere's magnetic barriers without slowing down. Some of them travel all the way to Earth's orbit before anything affects their motion. When neutral hydrogen atoms finally encounter our sun's radiation, they get ionized. Ionization means the radiation rips the electron away from the proton. Once ionized, these atoms become charged particles that our magnetic fields can control. The neutral hydrogen penetration shows that our heliosphere is not a perfect shield. It's very effective against charged particles, but neutral atoms slip through undetected. Our cosmic protection system has built-in vulnerabilities that let some interstellar material through. Common sense suggests that our heliosphere should stop all interstellar dust particles. These tiny grains are much larger than individual atoms. They should be easy targets for our solar wind to push away from our solar system. But spacecraft measurements tell a more complex story. Some interstellar dust particles do get blocked or deflected by our heliosphere, but others manage to penetrate into our solar system. The blocking is only partial, not complete. The dust particles that get through are usually the smallest ones. Teeny grains can sometimes slip past our defenses by following complex trajectories. They get nudged and deflected but not completely stopped. Eventually, some find paths that lead into our solar system. These dust particles carry information about the interstellar environment we're traveling through. By studying the dust that reaches our inner solar system, scientists can learn about the composition and history of our cosmic neighborhood. The partial blocking of interstellar dust shows that our heliosphere is a selective filter rather than a complete barrier. It blocks most things most of the time, but it's not impermeable. Some interstellar material always finds a way through. High-energy particles from deep space constantly bombard our solar system. Scientists call these cosmic rays. Most of them get blocked or deflected by our heliosphere, but the effectiveness of this blocking changes dramatically over time. The blocking follows a pattern that repeats every 11 years. This matches exactly with the sun's activity cycle. When the sun is highly active, fewer cosmic rays reach Earth. When the sun is quiet, more cosmic rays penetrate our defenses. During periods of high solar activity, the solar wind gets stronger and more turbulent. The stronger solar wind pushes our heliosphere boundaries farther outward. This creates a larger and more effective shield against cosmic rays. When solar activity decreases, the solar wind weakens. Our heliosphere shrinks inward. The weaker boundaries allow more cosmic rays to penetrate into our solar system. Earth receives higher doses of radiation from deep space. This cosmic ray modulation cycle affects everything from satellite operations to airline flights at high altitudes. The The sun's breathing rhythm directly controls how much dangerous radiation from the galaxy reaches our planet's neighborhood. High-energy particles from exploded stars race through the galaxy at nearly the speed of light. These galactic cosmic rays carry enough energy to damage DNA and disrupt electronic equipment. Without protection, they would make life on Earth impossible. Our heliosphere acts like a cosmic umbrella. It doesn't block all the dangerous radiation, but it stops most of it. The solar wind and magnetic fields deflect many cosmics away from our solar system. Others get slowed down and lose energy as they struggle through our cosmic defenses. Scientists have measured radiation levels inside and outside our heliosphere. The difference is dramatic. Inside our cosmic bubble, radiation levels are much lower than in the hostile environment of interstellar space. The heliosphere reduces cosmic ray intensity by a significant factor. This partial blocking creates a relatively safe zone for life to exist. Earth receives much less harmful radiation than it would if our solar system had no protection. The heliosphere doesn't eliminate all cosmic rays, but it reduces them to manageable levels. Our cosmic umbrella makes the difference between a radiation-soaked wasteland and a habitable solar system. Without this protection, complex life as we know it could never have evolved on Earth. The sun's activity follows an 11-year cycle. Sometimes it's very active with lots of solar flares and strong solar wind. Other times it becomes unusually quiet. Scientists call the quiet periods solar minimum. During solar minimum, the sun produces weaker solar wind. This weakens our heliosphere's ability to block cosmic rays. The reduced solar wind pressure allows our cosmic bubble to shrink inward. More dangerous radiation from deep space can penetrate our defenses. Satellite data shows that cosmic ray levels increase significantly during solar minimum periods. The radiation dose that astronauts receive goes up. Even airline pilots flying at high altitudes face increased exposure to cosmic rays. This increased radiation affects Earth's atmosphere in subtle ways. More cosmic rays create more charged particles in the upper atmosphere. Some scientists think this might even influence cloud formation and weather patterns. The sun's breathing rhythm directly controls how much protection we get from galactic radiation. When our star goes to sleep, our cosmic shield becomes less effective at keeping the dangerous galaxy at bay. Mars lost its global magnetic field billions of years ago. Without magnetic protection, the red planet faces the solar wind and cosmic radiation directly. This makes Mars an ideal natural experiment for understanding planetary protection. Spacecraft orbiting Mars have measured how the planet's atmosphere slowly leaks into space. Solar wind particles hit the Martian atmosphere and strip away atoms and molecules. The planet is gradually losing its air to space. But even Mars benefits from our heliosphere's protection. The atmospheric loss rate would be much higher if Mars were exposed to the full intensity of interstellar cosmic rays. Our cosmic bubble reduces the radiation bombardment that Mars experiences. Earth's early atmosphere might have suffered the same fate as Mars without multiple layers of protection. Our planet benefits from both Earth's magnetic field and the heliosphere's cosmic shielding. Mars shows us what happens when one of those protective systems fails. The comparison between Earth and Mars reveals how important our heliosphere is for atmospheric protection. Even planets without magnetic fields get some benefit from our solar system's cosmic umbrella. Earth enjoys protection from two separate defense systems that work together like partners. The heliosphere blocks most cosmic radiation from reaching our planet. Earth's magnetic field handles the threats that get through the first line of defense. Our planet's magnetic field creates a protective bubble called the magnetosphere. This magnetic bubble deflects charged particles around Earth. Solar wind particles and cosmic rays that penetrate the heliosphere often get turned away by our planetary magnetic shield. The two protection systems complement each other perfectly. The heliosphere reduces the overall radiation load. Earth's magnetosphere handles the remaining particles with surgical precision. Together, they create a double-layer defense that's more effective than either system alone. When both systems work together, they can deflect particles that neither could handle individually. A cosmic ray that partially penetrates the heliosphere might lose enough energy to be easily deflected by Earth's magnetic field. The combination provides redundant protection. This dual protection system explains why Earth has retained its atmosphere and developed complex life. The heliosphere and magnetosphere work as a team to maintain the safe radiation environment that makes our planet habitable. The Moon has no magnetic field and no atmosphere. Asteroids are just bare rock flying through space. These unprotected objects face cosmic radiation directly. They serve as natural radiation detectors that measure our heliosphere's effectiveness. Moon rocks brought back by Apollo astronauts contain records of cosmic ray exposure. Scientists can read this radiation history like a book. The data shows exactly how much cosmic radiation reaches our solar system despite the heliosphere's protection. Spacecraft visiting asteroids and comets measure radiation levels on these unprotected surfaces. The measurements confirm that even objects with zero protection benefit from the heliosphere's cosmic shielding. Radiation levels are lower than they would be in interstellar space. These natural experiments prove that the heliosphere provides a baseline level of protection for everything in our solar system. Even the most vulnerable objects get some benefit from our cosmic bubble. The protection isn't perfect, but it's significant. The radiation measurements from unprotected objects give scientists a way to calculate how much worse conditions would be without the heliosphere. Our cosmic umbrella makes every world in our solar system safer than it would be in the naked galaxy. Most people think our heliosphere is special to our solar system. This assumption turns out to be wrong. Many stars in the galaxy create their own versions of a protective bubble. Scientists call these stellar bubbles astrospheres. Just like our Sun, other stars blast streams of charged particles into space. These stellar winds race outward until they collide with the interstellar medium. The collision creates boundaries around star systems in the galaxy. Each star lives inside its own cosmic bubble. The basic physics works the same way across many environments in the universe. Hot stellar atmospheres accelerate particles to high speeds. These particles carry magnetic fields outward from the star. When stellar wind meets interstellar resistance, shock waves and boundaries form automatically. Observations suggest that astrosphere formation is a widespread stellar phenomenon. Red dwarf stars have astrospheres. White dwarf stars have astrospheres. Even massive blue giants create their own protective bubbles. The galaxy is filled with billions of these cosmic shields. Our heliosphere represents just one example of a common galactic structure. Every planetary system in the galaxy enjoys some level of protection from its parent star's astrosphere. Young, massive stars create astrospheres that dwarf our heliosphere. These stellar giants produce stellar winds that are hundreds of times stronger than our Sun's solar wind. Their cosmic bubbles can extend for many light years in all directions. Hot blue stars burn their nuclear fuel so rapidly that they live fast and die young during their brief lives. They create some of the most powerful stellar winds in the galaxy. These winds carve out enormous cavities in the interstellar medium around them. Red dwarf stars tell a completely different story. These small, cool stars produce weak stellar winds that barely extend beyond their planetary systems. Their astrospheres are tiny compared to our heliosphere, but red dwarfs live for trillions of years, so their small bubbles persist for vast amounts of time. The mass and age of a star determine the size and strength of its astrosphere. Massive young stars create temporary but enormous bubbles. Small old stars create permanent but tiny bubbles. Our sun falls somewhere in the middle of this cosmic spectrum. This diversity shows that stellar protection comes in many different forms throughout the galaxy. Every type of star creates its own unique version of cosmic shielding. Red giant stars and Wolf-Rayet stars produce stellar winds so powerful they create visible light shows in space. These evolved stars blast matter into space at rates that make our sun's solar wind look like a gentle breeze. The extreme winds create glowing nebulae that telescopes can photograph. The stellar winds from these extreme stars move so fast and carry so much material that they heat up the surrounding gas to thousands of degrees. Hot gas glows with its own light. The result is a beautiful nebula surrounding the star like a cosmic Christmas ornament. These nebulae reveal the astrosphere boundaries in spectacular detail. The glowing gas shows exactly where the stellar wind meets and compresses the interstellar medium. Astronomers can see the shock waves and turbulent mixing zones with their own eyes. Some of these stellar wind nebulas stretch across multiple light years. They're so bright and colorful that they rank among the most beautiful objects that telescopes can photograph. The extreme stellar winds turn invisible astrosphere physics into visible cosmic art. These glowing bubbles prove that our heliosphere's invisible boundaries become spectacular light shows around more powerful stars. The same physics that protects our solar system creates some of the galaxy's most stunning visual displays. Binary star systems create cosmic collision zones where two stellar winds meet head-on. Each star produces its own stellar wind racing outward at high speed. When these winds collide in the space between the stars, the results are spectacular and violent. The collision zone creates a shock wave structure unlike anything found around single stars. Hot gas gets compressed and accelerated to extreme temperatures. The collision zone glows brightly in X-rays that space telescopes can detect from thousands of light years away. The shape of the collision zone depends on how strong each stellar wind is. If both stars have similar wind strengths, the collision zone sits halfway between them. If one star has a much stronger wind, it pushes the collision zone closer to the weaker star. As the two stars orbit each other, the collision zone spirals and twists through space. The moving collision creates a spiral shock wave pattern that astronomers can track over time. The entire structure rotates like a cosmic pinwheel made of hot plasma. Binary stellar wind collisions show that astrospheres become much more complex when multiple stars share the same space. Instead of simple bubbles, binary systems create dynamic collision zones that change constantly as the stars orbit each other. The Hubble Space Telescope and other advanced instruments have achieved something remarkable. They can actually photograph the boundaries where stellar winds meet interstellar space around nearby stars. These images show astrosphere structures in unprecedented detail. The photographs reveal that astrospheres have complex shapes that depend on the star's motion through space. Fast-moving stars create bow shocks ahead of them and long tails behind them. The images look like cosmic teardrops racing through the galaxy. Some of the clearest astrosphere images come from red giant stars with very strong stellar winds. The boundaries are bright enough and large enough for telescopes to resolve them directly. Astronomers can see the exact shapes and sizes of these cosmic bubbles. These direct observations provide crucial data for testing theories about how astrospheres work. Scientists can compare their computer models with actual photographs of real astrosphere boundaries around other stars. The ability to photograph astrospheres around other stars gives astronomers a unique perspective on our own heliosphere. By studying stellar bubbles throughout the galaxy, scientists gain insights into the cosmic protection system that shields our own solar system. Our heliosphere doesn't stay the same size all the time. It grows larger and smaller in a regular pattern that repeats every 11 years. This cosmic breathing follows the sun's own activity cycle with perfect timing. During solar maximum, our star becomes hyperactive. Solar flares explode from its surface. The solar wind gets stronger and more turbulent. The increased wind pressure pushes our heliosphere boundaries farther outward into interstellar space. When the sun enters solar minimum, everything calms down. Fewer solar flares occur. The solar wind weakens dramatically. Without strong wind pressure, our cosmic bubble shrinks inward. The heliosphere contracts like a deflating balloon. Scientists can track these size changes by measuring cosmic ray levels reaching Earth. When the heliosphere expands, fewer cosmic rays penetrate our defenses. When it contracts, more dangerous radiation from deep space reaches our solar system. This 11-year breathing cycle shows that our cosmic protection is not a static shield. Instead, it's a dynamic system that pulses with the rhythm of our star's magnetic heartbeat. Billions of years ago, our sun was a very different star. Young stars burn hotter and produce much stronger stellar winds than older stars. The early sun created a heliosphere that was probably much larger than today's cosmic bubble. As stars age, they gradually lose mass and energy. Nuclear fusion in the sun's core becomes less efficient over billions of years. The solar wind weakens as our star slowly burns through its hydrogen fuel supply. Our heliosphere has been shrinking for billions of years. This long-term shrinking may have affected Earth's climate throughout geological history. A larger heliosphere in the past would have blocked more cosmic rays from reaching our planet. Changes in cosmic ray levels can influence cloud formation and atmospheric chemistry. Some scientists think variations in heliosphere size over geological time might correlate with major climate changes on Earth. Ice ages and warming periods could be partially influenced by our cosmic protection getting stronger or weaker over millions of years. Our sun's evolution guarantees that our heliosphere will continue changing over cosmic timescales. The cosmic protection that shields us today is just one snapshot in a billions-year story of stellar aging. Our solar system is not standing still in the galaxy. We're racing through space at high speed, passing through different regions of the interstellar medium. Each region has its own density, temperature, and magnetic properties that affect our heliosphere. When we travel through a dense interstellar cloud, the extra pressure compresses our cosmic bubble. The heliosphere gets squeezed from all sides like a balloon being pressed between hands. Our protection shrinks and becomes less effective at blocking cosmic rays. Moving into a thin region of interstellar space has the opposite effect. Lower external pressure allows our heliosphere to expand outward. The cosmic bubble grows larger and provides better protection from galactic radiation. These changes happen over timescales of thousands to millions of years. Our solar system might spend tens of thousands of years crossing through a single interstellar cloud. During that entire time, our cosmic protection remains compressed and weakened. The interstellar environment acts like cosmic weather that affects our heliosphere's performance. Different galactic neighborhoods create different levels of protection for our solar system as we journey through space. In about 5 billion years, our sun will begin running out of hydrogen fuel in its core. When this happens, the star will undergo a dramatic transformation that will completely change our heliosphere. The sun will expand into a red giant star. Red giant stars produce stellar winds that are hundreds of times stronger than our current solar wind. These powerful winds will inflate our heliosphere to enormous proportions. Our cosmic bubble will grow so large that it might extend several times farther than today's boundaries. The expanded heliosphere will provide unprecedented protection from cosmic rays. Galactic radiation will be almost completely blocked from entering our solar system. But this enhanced protection will come with a terrible cost for the inner planets. The red giant sun will be so large and hot that it will probably vaporize Mercury and Venus. Earth might barely survive at the edge of the expanded solar atmosphere. Our planet will become a scorched wasteland despite the improved cosmic ray protection. This future transformation shows that our heliosphere's evolution is tied directly to our star's life cycle. Enhanced cosmic protection will arrive too late to save the worlds that currently benefit from our more modest cosmic bubble. Ancient ice cores and rock layers preserve chemical signatures that reveal past cosmic ray levels reaching Earth. These geological records work like cosmic ray detectors that have been recording data for millions of years. Scientists can read this natural archive to learn about heliosphere changes. When cosmic rays hit Earth's atmosphere, they create specific radioactive elements. These cosmic ray markers get trapped in ice sheets and sediments. Higher concentrations indicate periods when more cosmic rays penetrated our cosmic defenses. The geological record shows that cosmic ray levels have varied significantly throughout Earth's history. Some periods show much higher cosmic ray exposure than today. Other periods show lower levels. These variations reflect changes in our heliosphere's protective effectiveness over time. Climate scientists are discovering correlations between cosmic ray levels and major climate shifts in Earth's past. Periods of high cosmic ray exposure sometimes coincide with cooling trends. Low cosmic ray periods sometimes align with warmer climates. These correlations suggest that our heliosphere's changing protection may have influenced Earth's climate evolution over geological time. Our cosmic shield hasn't just protected life. It may have helped shape the environmental conditions that allowed complex life to evolve. The heliosphere is completely invisible to human eyes and most telescopes. It's made of charged particles and magnetic fields that don't emit light. For decades, scientists could only theorize about its structure without being able to see it directly. But space scientists found an ingenious solution to this problem. They discovered that neutral hydrogen atoms from interstellar space create a faint glow when they hit solar wind particles. This collision produces special light that space telescopes can detect. When neutral hydrogen atoms enter our heliosphere, they eventually collide with solar wind particles. These collisions strip electrons from the hydrogen atoms and create a brief flash of ultraviolet light. The pattern of these flashes reveals the shape and structure of our cosmic bubble. Space telescopes can map these faint light signals to create images of the entire heliosphere. The technique works like cosmic echolocation. Scientists can see our invisible protection by watching how interstellar atoms light up when they hit our solar wind. This neutral atom imaging has revealed that our heliosphere is not a perfect sphere. Instead, it's distorted and asymmetric, shaped by our motion through interstellar space and the sun's changing magnetic field. Cosmic rays from deep space constantly bombard our planet. When our heliosphere gets stronger, fewer cosmic rays reach Earth. When it weakens, more cosmic rays penetrate our defenses. This makes cosmic rays perfect natural probes for studying our cosmic protection. Scientists have built cosmic ray monitoring stations around the world. Some sit on high mountains where the thin atmosphere provides less shielding. Others are buried deep underground to filter out everything except the most energetic particles. The most sensitive detectors use networks of particle counters spread across large areas. When a high-energy cosmic ray hits Earth's atmosphere, it creates a shower of secondary particles that spread out over several miles. The detector networks can track these particle showers in real time. Ground-based cosmic ray measurements provide continuous monitoring of our heliosphere's protective effectiveness. Changes in cosmic ray intensity tell scientists when solar wind strength varies or when our cosmic bubble encounters different regions of interstellar space. This Earth-based monitoring system gives scientists a way to study our heliosphere's behavior over many years without needing expensive spacecraft missions. Our planet itself serves as a giant cosmic ray detector. No single spacecraft can observe the entire solar wind system by itself. Solar wind conditions vary dramatically with location and time. Scientists needed a better way to understand how solar wind behaves across our entire solar system. The solution was to coordinate observations from multiple spacecraft at different locations. When several probes measure solar wind properties simultaneously, scientists can create three-dimensional maps of our cosmic bubble's interior structure. Modern spacecraft carry sophisticated plasma measurement instruments. These devices can measure particle density, temperature, speed, and magnetic field strength with incredible precision. Each spacecraft sends its data back to Earth, where computers combine all the measurements. The multi-spacecraft approach has revealed complex solar wind phenomena that single missions missed. Scientists discovered that solar wind streams interact and collide as they travel outward from the sun. Fast streams catch up to slow streams and create compression regions. This distributed observation network gives scientists their most detailed view of how our heliosphere works from the inside. Multiple spacecraft working together provide a level of understanding that no single mission could achieve alone. Starlight carries hidden information about everything it encounters during its journey through space. When light from distant stars passes through the interstellar medium near our solar system, it picks up chemical fingerprints that reveal the local cosmic environment. Different elements in interstellar space absorb specific wavelengths of ultraviolet light. These absorption lines work like chemical barcodes that identify what elements exist in the space between stars. Advanced space telescopes can read these cosmic barcodes with incredible precision. By analyzing absorption lines in the ultraviolet spectrum, scientists can determine the density, temperature, and chemical makeup of the interstellar material surrounding our heliosphere. This reveals the external conditions that shape our cosmic bubble's boundaries. The Hubble Space Telescope has been particularly valuable for this type of analysis. Its ultraviolet detectors can measure absorption lines from hundreds of nearby stars. Each measurement provides a sample of the interstellar medium in a different direction from our solar system. This stellar spectroscopy technique gives scientists a way to map the interstellar environment around our heliosphere without sending spacecraft beyond our cosmic bubble. Distant starlight becomes a probe that samples the galactic neighborhood we're traveling through. NASA's IBEX satellite represents a completely new approach to studying our heliosphere. IBEX stands for Interstellar Boundary Explorer. This specialized spacecraft hunts for particles that exist only in the boundary regions where our solar system meets interstellar space. The satellite detects high-energy neutral atoms that form when solar wind particles collide with interstellar material at our heliosphere's edges. These collisions create neutral atoms moving at incredible speeds. Most other spacecraft cannot detect these special particles. IBEX has discovered unexpected features in our heliosphere's structure. The satellite found a bright ribbon of high-energy neutral atoms stretching across the sky. This ribbon reveals where our heliosphere's magnetic field interacts most strongly with the interstellar magnetic field. The spacecraft orbits Earth but looks outward toward the edges of our solar system. Its detectors can measure the direction and energy of incoming neutral atoms. This information reveals the detailed structure and dynamics of our cosmic bubble's boundaries. IBEX has revolutionized our understanding of how our heliosphere interacts with interstellar space. The mission proves that specialized instruments designed for specific particles can reveal cosmic structures that general-purpose telescopes cannot detect. The Voyager spacecraft gave us our first glimpse of interstellar space, but they were never designed for heliosphere research. They carried instruments built for studying planets, not cosmic boundaries. Future interstellar missions will be purpose-built for exploring our cosmic protection system. Next-generation spacecraft will travel much faster than the Voyagers. Advanced propulsion systems will cut travel time to the heliosphere boundaries from decades to just a few years. Faster missions mean scientists can study multiple boundary crossings within a single career. These specialized probes will carry instruments specifically designed to measure heliosphere physics. Advanced plasma detectors, magnetic field sensors, and neutral atom imagers will provide unprecedented detail about boundary structures and dynamics. Multiple spacecraft will be launched simultaneously toward different parts of our heliosphere. This coordinated approach will reveal how our cosmic bubble varies with direction and time. Scientists will finally understand the three-dimensional structure of our protection system. Purpose-built heliosphere missions will transform our understanding from accidental discoveries to systematic exploration. The next generation of interstellar probes will be humanity's first deliberate ambassadors to the cosmic frontier. Our sun's north and south poles remain largely mysterious to scientists. No spacecraft has ever flown directly over either polar region. This massive gap in our knowledge affects our understanding of how the heliosphere forms and behaves. The solar wind that creates our heliosphere flows differently from the sun's polar regions than from its equatorial zones. Polar solar wind is faster and more uniform than equatorial wind, but scientists can only observe the polar wind from a distance using remote sensing techniques. Future solar polar missions will finally give us direct measurements from above the sun's poles. These spacecraft will need to travel far out of the plane where planets orbit to get a clear view of the solar poles. The journey will require advanced propulsion and navigation systems. Polar observations will reveal how the sun's magnetic field connects the polar regions to the heliosphere's overall structure. Scientists expect to discover that polar processes play a crucial role in shaping our cosmic protection, that we've never been able to study properly. Understanding the Sun's polar regions will complete our picture of how stellar activity creates and maintains the heliosphere. These missing puzzle pieces are essential for predicting how our cosmic protection will evolve over time. Communication delays make current spacecraft missions frustratingly slow to respond to interesting discoveries. Radio signals take hours to travel between Earth and the outer solar system. By the time scientists see interesting data and send new instructions, the spacecraft may have already moved past the phenomenon. Future missions will carry artificial intelligence systems capable of recognizing important discoveries autonomously. These AI explorers will analyze incoming data in real time and automatically adjust their observation plans when they detect something unusual or unexpected. AI spacecraft will be programmed with scientific priorities and decision-making algorithms. When the AI detects a boundary crossing or unusual magnetic field structure, it will automatically switch to high-resolution observation mode. The spacecraft will focus its instruments on the most scientifically valuable targets without waiting for human commands. Autonomous exploration will be especially valuable for studying dynamic heliosphere phenomena that change rapidly. Shock waves, magnetic reconnection events, and turbulent boundary layers happen too quickly for Earth-based mission control to respond effectively. AI-controlled missions will multiply the scientific return from heliosphere exploration by capturing transient events that human-controlled spacecraft would miss. Artificial intelligence will become our cosmic detective, always alert for unexpected discoveries at the edge of our solar system. Nuclear fusion propulsion represents the next revolution in space travel. Fusion rockets will be hundreds of times more powerful than current chemical rockets. This incredible power will allow spacecraft to reach speeds that make true interstellar exploration possible for the first time. Fusion-powered spacecraft will be able to travel far beyond our heliosphere into the deep interstellar medium. These missions will study multiple interstellar clouds that our solar system will encounter during its journey through the galaxy. Each cloud has different properties that affect our cosmic protection. The high speeds achievable with fusion propulsion will enable spacecraft to overtake our solar system's motion through the galaxy. These fast probes will scout ahead to study the interstellar environment that we're approaching. They'll provide advance warning about changes in cosmic conditions. Fusion missions will be capable of exploring the bow shock that forms ahead of our solar system as we move through interstellar space. This structure extends so far ahead of us that no other propulsion technology could reach it within reasonable mission timelines. Nuclear fusion will transform heliosphere research from studying our immediate cosmic neighborhood to exploring the broader galactic environment that shapes our protection. These missions will reveal how our heliosphere interacts with the larger universe around us. Most exoplanet research focuses on finding Earth-like worlds in habitable zones around other stars. But scientists are missing a crucial factor in planetary habitability. Do these exoplanets have astrospheres that protect them from galactic cosmic radiation like our heliosphere protects Earth? Future space telescopes will be powerful enough to detect and study astrosphere boundaries around nearby star systems. These observations will reveal which exoplanets benefit from stellar wind protection and which ones face the full fury of galactic radiation without any cosmic shielding. Advanced telescope arrays will combine the light-gathering power of multiple spacecraft working together. This coordinated approach will provide the sensitivity needed to detect the faint signatures of astrosphere boundaries around distant stars. The technique will work like a giant virtual telescope spanning huge distances. Studying exoplanet astrospheres will add a new dimension to the search for habitable worlds. Scientists will be able to assess not just whether an exoplanet has liquid water, but also whether it has adequate cosmic radiation protection for complex life to survive and evolve. This research will help scientists understand whether Earth's combination of magnetic field protection and heliosphere shielding is common or rare in the galaxy. The answer will profoundly influence estimates of how many potentially habitable worlds exist in our cosmic neighborhood.